Hello viewers, welcome to CAE for You. In practical product design, stress risers, like sudden section changes and cutouts, are unavoidable. They can have significant impact on the fatigue life of the component. There are also features which are meant to aid fitment, or avoid sharp edges, to prevent injuries. These are small features which could cause significant issues while meshing, in terms of number of elements and its quality. Many times CAE engineers have to take a decision on which features to be removed and which features to be retained. It is necessary to understand their effects for efficient computational modeling. Let us understand the effect of stress concentration with the classical example of plate with a hole. In the picture we could see that there could be a fillet, which contributes to the stress redistribution and hence reducing the stress concentration. Whereas a chamfer at the end of the pipe might be helpful in terms of fitment or to avoid sharp edge preventing injuries during handling. For simulation, we will consider a square plate of size 200 mm by 200 mm with centrally located hole of dimension 10 mm. We will consider the thickness of the plate to be 5 mm. We will consider two-hole configuration, one with a square hole and another with a circular hole. The square hole represents zero filler radius, which means we will simulate a very sharp corner, and on the contrary, the circular hole represents the maximum fillet radius that is possible. The lines shown are the partition lines of the geometry for creating structured mesh, and also we provide a buffer zone near the holes so that we will be able to see the effect of mesh refinement. Looking these cases closely, we observe that the geometry and the loading, along with the boundary condition, exhibit 1/4 symmetry. So it is sufficient to just model 1/4 of the geometry and adjust the loading and boundary conditions accordingly. The nature of the loading and the stress pattern is expected to show a plane stress condition. So it is sufficient to model only quarter 2D geometry, and we can apply the symmetry conditions by constraining the central plane. For a 2D case it would be normal to corresponding plane as shown in the picture. Though we refer it as plane in physical sense, it will be a line in the computational model. We will use the same boundary conditions and the loading conditions for both the cases so that it can be compared easily. It is important to understand the mesh convergence, particularly near the cutout. So we have chosen a characteristic elements of 2, 8, 16 and 32 number of elements in the buffer zone. As we see the mesh, it could be easily observed that, in the far field, uniform stress is expected, so the number of elements can still be lesser. However, in order to avoid any stress jumps, we will still maintain reasonable fine mesh. Higher order quad element was used for this simulation for better accuracy and computational efficiency. The geometry and mesh was created using GMSH. Let us look into the boundary conditions and the loading conditions, which will be used for the simulation. The plate is actually loaded in X direction, so the nodes along the X maximum was selected to create pressure load normal to the Y-axis. And in the same way, Y displacement has been set to 0 along the X-axis to simulate symmetry along the X-axis. Then X displacement has been set to 0 along the Y-axis to simulate symmetry about Y-axis. Pressure loading is preferred for this case because it is area normalized and we don't need to worry about the geometric modifications which were made due to symmetry. Simplified hand calculation has been done to arrive at the expected displacement at the far field so that it can be compared with the result that will be obtained from FEA simulation. For this analysis we have considered a far field pressure load and hence the stress of 100 MPa. We found that the expected far field displacement is about 0.0476 mm. As we did for the square cutout, we have done meshing with the same characteristic elements for the circular cutout also, so that the results are comparable. The simulation was carried out using Calculix. We will first consider the displacement plot and expect a linear deformation along the loading direction. We could see the displacement plot for both the circular cut-down and the square cutout geometries. The normal displacement has been provided at the far field region, which is considered to be the father's location from the center of the hole, and it will be used to compare with the value that we have calculated previously. We could clearly see that very close correlation between the predicted displacement to the values that we have calculated. Let us look into the typical stress plot. We expect that the stress be more concentrated around the cutouts because those are the stress razor points, and as a move away from the geometric discontinuities we expect the stress to be more uniform, and this is exactly replicated from the simulation result. Let us take a closer look at the peak stress values to understand the behavior due to mesh refinement. As we see for the coarse mesh, the peak stress is contained within one element. However, the value appears to be attenuated so quickly. As we increase the mesh density, the peak stress becomes more concentrated and moves towards the corner of the square cutout. This is exactly in line with the expected physical behavior. So we infer that the simulation represents the actual behavior of the component under the given loading and boundary condition. Further, it is interesting to observe the peak stress values keep climbing. Let's look into the stress levels for the circular cutout. We observe that though for coarse mesh the stress is contained within single element. As we refine the mesh near the hole, the peak stress don't increase significantly, which indicates there is a quick convergence of peak stress, in this case to the expected value. That is, even for coarse mesh the results are reasonably accurate. Viewers can separately verify that the expected peak stress near the circular cutout, for this case, is about 300 MPa. Let us put together the peak stress values for the circular cutout and the square cutout. We observe that the highest stress occurring near the square hole is not a numerical artifact. In fact, FEA actually tries to predict what has been supplied to it. In this case, it is actually chasing infinite stress as we keep refining the mesh. It can be observed that the peak stress will never become mesh independent. If defeaturing can't be avoided, then attenuated stress levels can be used with correction factor. Correction factors could be separately arrived from simulations. On the contrary, the fixed stress of circular hole shows very quick convergence to the expected stress value. At the first look, it appears even for coarse mesh the stress values are significantly accurate. Taking a deeper look, the mesh sensitivity trend actually shows a strange behavior, since the averaging of stress in coarse mesh will result in lower stress levels. The mesh refinement should actually show a upper bond convergence, but the results show lower bond convergence. In this case, it is difficult to get the contributor. In general, it is easy to predict the behavior of pure elements, but in some software to increase efficiency, element expansion with special treatment are employed. For example, 1D, 2D elements are expanded as 3D elements internally. So simulation results should be always dealt with caution even if the results appear correct unless extensively validated. Now let us look at the normal stress distribution with respect to the distance from hole center. The result of zero filler radius to full fillet radius is compared to understand the attenuation behavior of the peak stress for both circular and square hole. The normal stress value is provided along the x is equal to 0 line and plotted the stress approximately at a distance of around 10% from the center of the hole. The stress value coincide, and at about 20% this stress is very close to far field stress. Establishing a correlation factor with far field stress can be an economical option in absence of any complex stress interactions. To conclude this study, we see that the present work demonstrates good capabilities of open-source software Calculix in predicting high-gradient stress field around holes with reasonable computation cost. This calculation can be critical for life prediction of machine parts. For simple stress risers, establishing correlation factors can enhance computational efficiency in terms of hardware and time for computations. Simple correlation may not be possible in complex situation, and full-featured modeling may be warranted. Peak stresses are all not always artifacts, but they could very well reflect improper inputs. They should be ratified with the care by the simulation engineer. Using elastic plastic analysis is a wrong modeling practice to show bounded stress levels. It may not add value than increasing computational cost and time. Proper treatment of stress during design phase has resulted and can result in avoiding product failures, leading to life and economic losses. Thank you for watching. Hope you liked our video. Stay tuned for more videos.